Okay, so my plan for today is to finish the proof for the volume of the permutahedron. So just to remind you, we defined the simplex delta ij, the edge delta ij to be the convex hull of the unit vectors ei and ej. And then we proved that the permutahedron pi n is the Minkowski sum of all of these segments. Right? And we can then plug into the machinery of mixed volumes to say that the volume of the permutahedron is the sum of, what we do is we have to take all the possible n tuples of things like this and do the mixed volume of that. So we take an n tuple delta I1 J1 up to delta IN Jn, where I1 is less than J1 up to IN less than J. Okay? So we talked about this, and then what I'm about to prove to you, which I promised I would, is the following thing. That the volumes of these delta 1 J1 up to delta I and Jn are very nice. So we said that the volume is going to be 1 over n minus 1 factorial if A1 J1 up to I n Jn are a spanning tree of the complete graph. And 0 otherwise. Does anybody see a mistake in what I wrote so far? For one thing, you can't have a spanning tree of Kn that has n edges, because you know that spanning trees have n minus 1 edges. Okay? So that tells me that this statement must be wrong, and I should go all the way to n minus 1 only, which probably means that I should do this up until n minus 1, and this I should do this up to n minus 1. And do you guys remember why that is? So that's right. The point is that the volume is n minus 1 dimensional, because even though the permutahedron lives in n dimensions, it's really n minus 1 dimensional, and that's why we only take n minus 1 things here. And I'm realizing that another thing that I made a mistake on is that I'm forgetting an n minus 1 factorial here that just comes from the formula for the for the volume of a Minkowski sum. So remember that formula involved these factorials, and I forgot to put it here. Okay. Now the point is that as soon as I prove this formula for you for the mixed volumes, then we're going to be able to conclude exactly what this is, right? Because this term is going to be 0 a lot of the time, and when it's not 0, then it's going to be exactly n minus 1 factorial times 1 over n minus 1 factorial. So I'm just going to be summing a bunch of 1s, and I'm going to get a 1 every time I have a spanning tree of Kn. Okay? So what I'm going to get then is the number of spanning trees of the complete graph So this is going to be implied by the proposition. Okay. And then we already discussed that this number is beautiful, is very nice and explicit. It is just n to the n minus 2. Okay. And this goes through some combinatorics. This is not supposed to be a trivial fact. It's something. It's a nice fact in combinatorics that if I have time, I'm going to prove to you as well. Okay. So our main goal is to do this. Now there is one thing that I need to remind you of, which is that there is this subtlety of volume versus relative volume, right? And we care about that subtlety because, like we said, the permutahedron is not full dimensional. And so when I say volume here, I'm being a little bit careless because what I really mean is relative volume. Okay? And so to get the actual volume, I'm going to have to do the following thing. So that's what I drew. That's why I drew a picture for you here of, this is the permutahedron pi 3, the black polytope. The black polytope, it's a hexagon. And it lives on the plane x plus y plus z equals 3. Okay? But I really want to think of the permutahedron as being a full-dimensional polytope. And so then what I'm going to do is that I'm going to take the projection onto the xy plane. Okay? So I'm just going to consider the projection that takes this black polytope and just looks at its vertical shadow. Okay. So this is the projection. Well, I shouldn't call it pi because it's a permutahedron. But what else do you call a projection? I don't know. P, I guess. I probably have p's there too. I don't know. Projection P. Projection P, and what this projection does is that it just forgets the last coordinate. And so, well, okay, so really, maybe you should be thinking of this more as going from R3 to R2, okay? So I'm looking at the shadow, but then I'm looking really as being living on the horizontal plane only, okay? And so this is my shadow, which I get by taking the point, let's say, x1 up to xn, and just forgetting the last coordinate. Okay? And so you see that's exactly what I did here. So as I forget the last coordinate, you have to kind of rotate the picture around. But 102 becomes 10, 201 becomes 20, this becomes 21, 12, 02, and 01. Okay? Now, okay, so then this maybe we can call P of pi 3. But the point that I want to make is that here we're doing relative volumes, and it's a little bit subtle because we have to pay attention to the lattice that lives there. And for example, we saw that this guy has relative volume 3, even though the actual volume is not 3 if you were to compute it. Okay? But if you see what happens with this projection, you get that the volume is exactly 3. Okay? And so that's the advantage of this projection, that instead of computing the relative volume of the permutahedron, I can compute the actual volume of the projection of the permutahedron. The reason being that the lattice on this plane becomes the standard lattice on here. Okay? And so that's what I'm going to do. Okay. So again, when I say this mixed volume, really what you should be thinking is more like a relative volume. I think maybe this is going to be clearest if I just do an example. So let's do the following thing. Let's say that you want to compute the mixed volume of the following thing. Delta 13 delta 2, 6, delta 1, 4, delta 3, 6, and delta 2, 5. Okay. Well, let me show you what happens if we. I mean, what is the system of equations that we get? We get number of isolated, or maybe let's do it over here. Number of isolated solutions to a system of equations. Okay? And remember that what we're supposed to do is take each one of these polytopes and make a polynomial out of it. So for example, this polytope only has two vertices, which are the unit vector in direction 1 and the unit vector in direction 3. So that means that the corresponding equation is going to look something like x1 plus no x2 plus something x3 plus no x4 plus no x5 plus no x6 equals 0. Okay, that's the first equation. The second equation is going to say x2 plus x3, x4, x5, let's see, x4, x5, x6 equals 0. Then 1, 4 is going to look like this. x1 plus x2 plus x3 plus x4 equals 0. Then this one, 3, 6, I'm going to get something x3 plus something x6 equals 0. And then finally, this one says that something x2 plus something x5 equals 0. Okay? Now, what is the system? The system is a 5 by 6 system of equations. Okay? And so how can it have isolated solutions if you have more? You have 6 variables and you have 5 equations. So that means that you don't have a finite number of solutions. Okay? So something is going wrong here. And what's going wrong is precisely this subtlety because really what we have to do is not compute here, but compute in the projection. Okay? So what's the point? The point is that this pi 3 is simplex delta 1, 2 plus simplex delta 1, 3 plus simplex delta 2, 3. Okay? So this is, let's see, one. Let me get the axes right. So this is the 1 axis, this is the 2 axis, and this is the 3 axis. And so this is 1, 2 plus 1, 3 plus 2, 3. Okay? But then when I tilt my polytope over, that's also going to tilt these things over. Okay? So what does 1, 2 become? The polytope 1, 2 becomes still the polytope. Let's see, this is the 1 axis and this is the 2 axis. Okay? So 1, 2 is still 1, 2 because you didn't lose. That you didn't lose the third coordinate. What happens from here to here is that you lose the third coordinate. But you see now what happens to 1, 3. Well, 1, 3 looked like this, but now under the projection, 3 went to 0, and so this thing distorted my 1, 3, and now makes it this direction from, instead of having vertices E1 and E3, I have vertices E1 and 0. Okay, so maybe a better picture is like this. E1, E2 plus 1, 3 becomes 0, E1, and delta 2, 3, which looked like this, now that 3 got sent down, it's going to be the direction 0, E2. Okay? So I basically just, maybe to be consistent, let's say E1, E2, E1, E3, and E3, E2, and what happens is that I send E3 to 0, okay? But so what's the point that I'm trying to make here? The point that I'm trying to make is that really I'm trying to compute a relative volume here, and the way that I do that is that I compute the actual volume under the projection, okay? And that projection leaves 1, 3 alone, but now whenever you see a 6, the 6 coordinate is lost and it becomes a 0, okay? So let's denote it something like 2, 0, 1, 4, then 3, 6 becomes 0, and then 2, 5, where delta I0 is the convex hull of EI, and what used to be E6, but now it's 0. Okay? And this is the actual volume, and this is where I can actually apply Bernstein's theorem. Okay? And Bernstein's theorem says, okay, we'll keep the same equations, but what happened? Well, what happened is that now instead of having 2, 6, you have 2, 0. So instead of having a monomial x2 and a monomial x6, you have a monomial x2, and if you have exponent 0, that means you just have a 1. Okay? I mean, the point is that x to the 2, 0 is like, do you guys see why it's a 1? I mean, for example, this is what 2, 0 might look like. This is E2 and this is 0. And so this gives me an x1 to the 0, x2 to the 1, so that's an x2. And this gives me an x1 to the 0, x2 to the 0, which is a 1. Okay? So the effect of that is that whenever you see an x6 there, it just becomes a 1. Okay? So this becomes a 1, and this becomes a 1. And that's really what I want to compute. Okay? So let me just put the constants to the other side. And so what we're going to get is, this is 0, this is a constant, this is 0, this is a constant, and this is 0. And what I'm trying to do is figure out how many isolated solutions this system has if my asterisks are generic numbers. Okay? And these things really are equal to each other. Okay? Except for this factor of 1 over something factorial. So remember that factor appears in Bernstein's theorem, so you get this factor. Okay? So the point is basically that you're going to look at this system, and we need to argue the following. We need to argue that if we have a spanning tree, then this system has exactly one solution, isolated, non-zero. I mean, no coordinates are 0. And if this is not a spanning tree, then this system has no isolated solutions. That's what I need to argue. Okay? So let's go ahead and do that. Let's draw the corresponding graph. Maybe let's make it big over here. So maybe this is 1, 2, 3, 4, 5, and 6. Okay? And now what I need to do is I need to take each one of these edges and draw it into that graph. So I draw the edge 1, 3, and I get this. I draw the edge 2, 6, and I get this. I draw the edge 1, 4. I draw the edge 3, 6. And I draw the edge 2, 5. Okay? And then I ask myself, is this a spanning tree? And it is a spanning tree, right? It touches every vertex, and there's no cycles, so it's a spanning tree. So therefore, we must be able to argue that this system has one unique isolated solution in c minus 0 to the 6 to the 5. I guess I lost a variable. I lost my variable x6. So, okay. So first, let's argue what happens if I do have a spanning tree. So 1. If I do have a spanning tree, if this is a spanning tree, then I want to argue that this has exactly one solution. Okay? And the way that I'm going to do it is the following. How can I mean, let's just do it. So here's the system of equations. Solve it. Okay? So just start solving it. Tell me what you can solve for. I'm sorry? So x2, I can solve x2. How do I get x2? Well, x2 is equal to something. And that gives me what x2 is. And x3 is equal to something. So that I know what x2 is, I know what x3 is. Okay? So that means that I know what this is, and I know what this is. After that, what? After that, well, x1 I can now solve for, given that I know what x3 is. Okay? So I can solve for x1. Then what? x5 I can solve for because I know what x2 is. So I do that. And what about x4? Now that I know what x1 is, I can solve for it. So you see how I'm kind of walking around this graph, yeah? Yeah?
Are you trying to argue that the incidence matrix is the matrix for that spanning tree, or are we already assuming that somehow?
The way that I drew, that's absolutely true. The way that I drew this graph is that I drew an edge whenever I had a delta ij here. So if I had a delta 1, 3 here, then I draw an edge 1, 3 in the graph. Okay? And that means that I have an equation here between 1 and 3. So if you're comfortable with this, you can think of this as being the incidence matrix, where here I have the vertices of the graph and here I have the edges of the graph. And you just have stars there. So it's a little bit of a strange incidence matrix, right? Because it's like the incidence matrix except for this weird sixth guy. So I should preface it with that. It was the incidence matrix until I messed with x6.
How do we see that it's correct, though, that incidence matrix, we change that, so that x6 is gone and it still represents that?
Well, let me make the argument of how we're going to do this. So now we know how to do it in this special case, but now let's try to generalize, okay? So how do I know that I can always do this? Well, let me ask you guys. Jimmy, looking at this picture, why did you give me 2 and 3 to begin with?
Because they're isolated variables.
They're isolated variables here. 2 and 3 are isolated. And in the graph, what does that mean? That they're connected to 6. Because these were the 6s. And so the isolated variables here are precisely the vertices connected to 6. Right? So I can solve for those no problem. Okay? So in step 1, I use this equation to solve for x2 and this equation to solve for x3. That's step 1. So step 1, I have this guy and I have this guy. So then, Michael, you told me what to do next. You told me you could do which ones? X1 and X5. X1 And the reason that you can do x1 is because it's connected to x3. Okay. And x5, the reason that you can compute that one, that you can solve for x5, is that you already know the value of x2, because that's connected to x2. Okay. So in the second step, these are the guys that I can get. Okay. And then Dilo told me, okay, now you can do x4 in the third step. Why? Because now x4 is connected to x1, and I already solved for x1 in the previous step. Okay. So I have to do this step by step, but the point is basically that I'm kind of starting with my special vertex, right? My sixth vertex. And then I'm going to kind of propagate the solutions along the tree. Okay. So first I can solve for the neighbors of this kind of root of the tree. So I solve for the neighbors, step 1. Then in step 2, I can solve for the neighbors of the neighbors. In step 3, for the neighbors of the neighbors of the neighbors. This should remind you of when you were finding diameters of graphs, right? This is exactly what it is. So in step I am solving for the vertices at distance I from the root. And because this is connected, that means that I can solve for everything. Okay? So that means that I have a unique solution. Do we agree? Yeah.
And if it's not a spanning tree, then it's not connected enough to be a complete solution.
But let me I'll get back to that in just a second, but we're not done, because if this is a spanning tree, then by what I just said, by blah blah blah, I have a unique solution. A unique solution, and if it's unique, then it's definitely isolated. Okay? But we not only need isolated, we need this. So remember that Bernstein's theorem counts solutions where no coordinate is equal to 0. So how can we argue that in this solution no coordinate is equal to 0?
Well, don't you start with things that are, in the first step you know that x2 and x3 are unequal to 0. And then you have these things that are linear combinations of other things that are non-zero, equaling to 0. So those things cannot be.
Exactly right. The point is that you cannot do it by induction on the steps. So we know that these stars are not 0. Why? Because they're stars, they're generic. And that means that the values of x2 and x3 are not going to be 0, because also I'm just dividing by these constants. So x2 and x3 are not 0. So step 1, that's fine. What about step 2? Well, in step 2, I'm getting that each new variable of step 2 is a constant multiple of a variable from step 1. And if you're a constant multiple and if the coefficient is not 0, that means that you don't get to be 0 either. If this is not 0, then this cannot be 0. And add up to 0. Okay? And so you can argue by induction on the steps that you never get any zeros here. So I have a unique solution, and it has no coordinate equal to 0. Okay? And therefore, the mixed volume is 1 over n minus 1 factorial. Okay? Because it's 1 over n minus 1 factorial times 1. Okay? Okay, so now tell me again what you were going to say, Jimmy.
No, I was going to say, if you don't have a spanning tree, then you don't have enough connectivity in order to solve your system of equations. Okay?
Exactly. So if you don't have a spanning tree, and maybe let's do an example. So how can I ruin this spanning tree? Let's take this. Let's take 1, 3 out, and put 3, 5 in. Okay. So instead of 1, 3, I'm going to put 3, 5. Instead of 1, 3, I have 3, 5. This is the same, but this equation changes. 2 x3 plus star x5 equals 0. Okay. So then what Jimmy's telling me is that, okay, I can take I can do the same thing, and in step 1 I can find the values of x2 and x3. In step 2 I can find the value of x5. Okay. But then I have no further information to figure out what the values of x1 and x4 are because the equations do not suffice. Right? I have one equation for two variables, x1, something x1 plus something x4 equals 0. So that's not enough information to get a unique solution. Okay? But the situation is even worse than that, actually, because in step 1, I find the values of x2 and x3. And in step 2, I find the value of x5. But the thing is that I can use it from 2, I get one value, and from 3, I get a different value. Why different? Because this is generic. And so the values are not going to work out to give me even any solution. Okay. Put differently, the problem is that precisely. Yeah, that's a very good point. You can just think of this as the system is underdetermined, and so you get a lower dimensional polytope, which is why it has volume 0. Yeah. Let me say what I was going to say, that you can also look at it as these 4 equations, the ones involving 2, 3, 5, and 6, give me an overdetermined system. Okay? And because the values are generic, in an overdetermined system, you're not going to get a solution. Okay, so 2, if this is not a spanning tree, then through the same blah, 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 I have no solution. And so therefore I get 0 over n minus 1 factorial. Okay. And that proves it. That proves this. Yeah?
I think that's kind of what bothered me about the original construction. If you give me just a generic spanning tree for the graph, and I were still an instance matrix, I would go to the system to be overdetermined and said there is no unique solution within this. And so you're saying that we can always do this and make it a
that's a good point. Again, if you're comfortable with incidence matrices, so what I had before was here are the vertices, here are the edges, right? Actually, even if you're not comfortable, you can pay attention, and I'm not saying anything too revolutionary here. I'm saying for each edge, I have 2 entries which say which vertices they are. Okay. Now the thing is that in a spanning tree, I have n minus 1 edges and n vertices. So that's an underdetermined system, and that means that's just the dimensions are not going to work out. But it's precisely because the polytope has the wrong dimension. I'm trying to find the 3-dimensional volume of a 2-dimensional thing, and that's not going to work out. If I go to the correct dimension, which is dimension 2, then I end up losing a variable. It's kind of like rooting a vertex, and through that procedure, I get a system that is just right and gives me a solution if and only if I have a spanning tree.
Another way to say it, I guess, from the algebraic side is you're looking for non-zero solutions. We know the solution space. We have a solution where x6 is not 0. We can still make x6 equal to 1. That's the same thing.
Right. Okay. So we're done. We proved it. We proved that the permutahedron has volume, well, equal to the number of spanning trees. We haven't proved that it's n to the n minus 2, but I really like this kind of thing. So to get to this, we really had to do a lot of different things, a lot of different arguments, and it's a very nice mix of algebra, combinatorics, geometry. How are we doing for time? Okay, so I thought actually it would be kind of unfair to rob you of the privilege of seeing this wonderful proof for the number of spanning trees, because it's a very nice result. So let's do the last step of this proof, which is this theorem, which I think is due to Cayley. I wrote it down here. Yeah. Theorem due to Cayley that the number of spanning trees of the complete graph is n to the n minus 2. And just to make sure that it's clear what we're talking about, if n is equal to 3, then the complete graph has 3 vertices and they're all connected. So that what spanning trees do I have? Well, I basically have to choose 2 of these guys. So I either do this, or I do this, or I do this. So that's 3 spanning trees, which is 3 to the 1. Okay. But it's important to notice that here I'm thinking of K3 as being numbered, right? Because if I just give it to you like this, you might think that these are the same tree. But they're not the same tree because these trees are numbered. So that's why they're different trees. Okay? Okay, so let's prove this. So I should tell you, there's different ways of proving this. There's actually a really beautiful algebraic way through some very nice linear algebra using the adjacency matrix. There's some very nice things you can do. But I want to give you, so if you're interested, I can tell you where to find that proof. But what I want to do is an elementary combinatorial proof, okay? Because the answer is very simple. N to the n minus 2 is a very simple number. For a combinatorialist, that's a very natural thing. You know, if you ask a combinatorialist, like in Jeopardy, right? What is n to the n minus n to the n minus 2? No, sorry. The answer is n to the n minus 2. That's, and then the question is, what is the number of what? Number of sequences A1 up to an minus 2, where each AI is a number between 1 and n. Right? That's the simplest question that I can think of whose answer is n to the n minus 2. Because you have n choices for the first one, n choices for the second one, up to n choices for the n minus second one. Okay, and then we want to prove that the number of spanning trees is also this. And so then what a combinatorialist will try to do is to find a bijection between these two sets, between these sequences and the spanning trees of Kn. And that's going to be our plan. So our goal is to find a bijection between these sequences, which, by the way, there's a this is the notation for that. N to the n minus 2. A set to a number is exactly this, but the point is that this is the set of sequences. Okay? And the spanning trees of Kn, which I can just think of, these are just trees on n vertices. Okay, labeled trees. On n vertices. Okay. And once I find this bijection, I'm going to be done. So that's the plan. And again, there's several different ways of doing this. I'll show you my favorite one. So let me show you first a map F from a tree to a sequence. Okay. So F is going to take a tree and spit out something called the code of the tree. Okay. And it's going to be like this. So I'll explain it to you, but at the same time I'll do an example. So you have some tree. And this tree is labeled, right? So maybe it looks like this. Okay, it's labeled with the numbers from 1 to 10. And then what I'm going to do is the following. So I start with a tree, and then what I'm going to do is, okay, I think at this point it's very important that you look up and see what I'm going to do. It's a bit of a movie. So I'm going to look at all the leaves of this tree. And a leaf is one of these dangling edges that has degree 1. So the leaves are 1, 5, 8, 2, 4, and 6. I'm going to take the largest one, 8, and I'm going to delete it. And I'm going to keep track of who it was dangling from. And I'm going to put that number down, 9. Okay? And then I'm going to repeat. So sequentially, I'm going to I really like this word, prune. I learned this word. I thought it was a mathematical word, but it's really what you do to a tree, right? You really prune this branch. Okay, so you prune the largest leaf and write down its neighbor. Its neighbor vertex. Okay? So let's keep doing this. So in the next step, what are the leaves? 5, 1, 6, 4, and 2. So then I'm going to prune 6. And I'm going to say that 6 was hanging from 7. Okay. Now in the next step, I have 1, 2, 4, and 5, and that means that I should prune 5. And that was hanging from 10. Okay. Now my leaves are 1, 4, 2, and 10. So that means that I should prune 10. And here you notice something important, that sometimes things that weren't leaves become leaves. So here 10 became a leaf, and so it's time to prune it. And that was hanging from 7. Okay. Now the leaves are 1, 4, and 2. 4 is the biggest, I prune it. And that's hanging from 3. Then I have 2 and 1, so I prune 2. And that's hanging from 3. Then it's 1 and 3, so I prune 3. And that's hanging from 9. Then I have 1 and 9. And so I prune 9. And that's hanging from 7. And then I stop. Why did I stop there? Instead of keeping pruning. I mean, I could say that I prune 7 and record a 1, so why didn't I do that? Well, the kind of cheap answer is that I already have n minus 2 letters, so I better stop there if my bijection is to work. Okay? So I need to stop there if this is going to work. So that's what I'm going to do. So stop when you have 2 vertices left. Sometimes proofs just force these things upon you. So stop when there are 2 vertices left. Okay? Okay. So one thing is very clear, I think, which is that F really does map from here to here. Okay? This clearly is a sequence of length n minus 2, and clearly every one of these numbers is between 1 and n. Okay? What is not at all clear is how this is supposed to be a bijection. Okay? And what do I need to do to prove that it's a bijection? Well, basically, it should be that no matter what sequence I give you of n minus 2 numbers between 1 and n, you are supposed to be able to tell me, and tell me uniquely, what tree that sequence comes from. Okay? So in other words, I need to give some kind of algorithm to undo this algorithm. Okay? So let's do that. Okay, so maybe one observation before I return is the following. How can you tell the degree of a vertex, like vertex 9, just by looking at that sequence? So I cover up the tree, and I'm really covering it up, and I ask you, what degree does 7 have? And you can't look at the tree, but you can look at this. It has degree 4. Why? Because first I pruned one of its guys, then I pruned another one of its guys, then I pruned another one of these guys, and then what? And then this is, if 7 hasn't been pruned, that means it's connected to somebody. Okay. So if I has degree D in the tree, then I appears D minus 1 times in the code of T. Okay? And that's a very important observation. Because you see, that observation lets us know very easily who the leaves are. Right? I mean, again, I cover this up and I ask you, who are the leaves of this tree? It's everything that doesn't appear. Right? If you have, a leaf is something of degree 1, so it's something that doesn't appear in the code. Okay. So then, let's take the code. And I'm going to try not to look at that board over there and just recover that tree. So what are the leaves? The things that don't appear here, right? So 1, 2, 4, 5, 6, and 8. Okay? So what was the first leaf to be pruned? Well, we chose to prune the largest one. So that means that the largest leaf we pruned must have been 8. And this must be its neighbor. Okay? So I say, find the largest leaf so far. So find the largest label missing from the code of T. So to recover T, I find the largest label missing from the code of T, and then I have to, that must have been the first pruned thing, so I have to connect it to the first neighbor. Connect it to first neighbor. Okay, so I'm going to try to more or less geographically copy these numbers down, but not look at what's connected to what. Okay, so it says 8 must have been the first thing I pruned, and it must have been pruned from 9. So I get to connect 8 and 9. Okay. Okay, and then I look and I say, what is the next leaf that I pruned? It must have been 6, right? And it must have been pruned from 7. Okay. Then what is the next thing that I pruned? It must be 5. Right? And it must have been pruned from 10. Then what? It's actually not. You might be tempted to say that it's 4, but it's not 4, and the reason is that 10 just became a leaf in this algorithm because 10 already has one connection, okay? And we know that 10 has degree 2 because it only appears twice here, once here. So 10 has degree 2, and if it's connected, if I already disconnected it once, then it must be a leaf right now, and that means that now it is ready to be put back into the tree. So 10 must be here and connected to 7. Then what? Then 4, right? I mean, I already. So maybe what I should have said is that. Maybe let me back up a step. The thing is that by putting 10 in my picture, I made it into a leaf, and so maybe I should have kept a running tally of the leaves that I had. So these were the original ones. Then I knocked this one off. Then I knocked this one off. Then I knocked this one off, and then in this step, 10 became a leaf. So I should have added it to the list of available leaves. Okay, and that's why I can knock it off. Okay, so I knock it off. Does 7 become an available leaf? No, because 7 is still appearing. Okay, so 7 doesn't go on the list. So that means that I have to look for the biggest number in this list. It's a 4. It's connected to 3. And I don't get to add 3 to the list because 3 is here. Okay, so then the next thing is 2. Oh, but wait, so 4 and 3 I should connect. Then the next available leaf is 2. I connect it to 3. And now 3 becomes free. So I knock off 2. I add 3 to my list of leaves. And I connect 2 and 3. Okay. Then my available leaves are 3 and 1.